a slightly more advanced version of differentiation. What you would what you would need to know is, for example, a sinusoid. So I think this is the most common thing we'll be working with. So let's see, here, and I have a sinusoid. Okay, so let's assume that actually does look like a sinusoid. And if I have the period of t, then my frequency is 1 over t. This is of course the time axis, this is t. Let's say it's a voltage, so I have v. Let's say the amplitude is 1 volt. So the equation for this, or let's say the amplitude is actually a, so we get some sense of what that means. So the equation of that voltage is actually a into what we just did, sine of 2 pi f is 1 over t, so I'm just going to put capital T into small t. Small t is a variable, it's changing with time. Okay, so that's what is the voltage curve. So if you look at the voltage curve, and based on what we have just spoken, we know that what I'm trying to get here is the derivative of d of voltage the same time as a function of time. There. Okay, so we know that when things are not changing, which is basically right at the top here, we know that the slope is 0. Here, even here, the voltage is not changing, the slope will be 0. We know here the slope will be the maximum. It's changing, but actually it's starting to slow down and come to 1. So actually it starts from a high value, slows down, goes through 0, and then here actually the slope has become negative. Here the slope is at least positive, here the slope is negative. It starts with a small negative value and then keeps becoming sharper and sharper. It goes faster and faster, becomes the maximum negative value here, then starts slowing down, then comes back to 0. So it actually starts here. This is where it reaches its maximum negative value. So actually it looks like a cosine waveform. So yeah, for those who know, the derivative is dv by dt is a into 2 pi by t into cos of 2 pi by t small t. Okay. This is frequency. I can also write this as a into 2 pi frequency into cos of 2 pi by t into t, 2 pi ft. Okay, so the exact expression is fine. It is what it is, but what is more interesting is if you can get an intuitive feel of this, and so let's quickly do that. So if I had a signal with a larger amplitude sine wave, then if I needed to get to that sine wave, the amplitude of my signal actually needs to be higher. I mean, I need to have a higher differential, because the slope here is higher than the slope here is higher than the slope of this waveform. So I start with a higher voltage, I still go through the 0 and the same signal. So that explains why a is there in my derivative as well. I'm sorry, from here. Okay, so now what about this relation with 2 pi f? So let's look at that also. So if I have a waveform that's slow, okay, I'm angling, but well, I'm getting used to this new tool. And if I have exactly the same amplitude, whether it's going faster, whatever, then again I can see that uh, even though it's the same amplitude, the speed at which I'm changing here is much slower than the speed I'm changing there. So it still means that the derivative is actually going to be faster, and that's why it's also proportional. The derivative is also proportional to the frequency, which is coming from here. 1 over t is frequency. This is also equal to a into sine of 2 pi f t. Okay. So these are the two things that are important, that the derivative of a sinusoid is proportional to the amplitude and it is proportional to the frequency that the signal is being fed at. And this is important basically because it connects to the capacitor, because in a capacitor my current is basically a function of the derivative of my voltage. So if my voltage is being fed at a higher frequency, then the current I will get, even though the amplitude of the voltage may be the same, is actually going to be higher. This one's frequency is higher, the current goes up as the frequency goes up, and that's important.